The cosmos holds a secret history written in faint whispers of light. We are now decoding the bizarre clues left over from the universe's explosive birth. By the end of this journey, you will see our cosmic origins in a completely new light. What force stretched the infant universe faster than light itself? And why do the oldest stars lack a key element they should possess? How many of our most basic assumptions about reality might be completely wrong? What does it truly mean to look back in time and see the dawn of everything? A persistent hiss haunted the radio telescope, an unshakable noise that defied all explanation. Two astronomers, Arno Penzias and Robert Wilson, pointed their massive horn antenna at the empty sky, yet this static remained constant and uniform day and night. They scrubbed the instrument clean, even evicting a pair of pigeons and their stubborn droppings, but the whisper persisted. This was no instrument error. They had accidentally stumbled upon the oldest light in the universe, the cosmic microwave background. It is the cooled and stretched remnant of the universe's fiery birth, a fossil glow that permeates all of space. Think of it as the lingering warmth from a colossal fireball, now cooled over billions of years to just a few degrees above absolute zero. This faint microwave radiation is the afterglow of the Big Bang itself, and it gives us our most direct baby picture of the cosmos. The most stunning feature of this ancient light is its profound uniformity. No matter which direction we look, the temperature of this background is almost exactly the same, varying by less than 1/100%. For a universe that today is filled with galaxies and vast empty voids, this smoothness is deeply strange. How could regions of space now separated by tens of billions of light years have achieved the same temperature when there hasn't been enough time since the beginning for light or heat to travel between them? This perfect uniformity is the first major clue that the early universe was not like the one we see today. It is the foundational evidence for our entire modern understanding of cosmology, the bedrock upon which we build our theories of cosmic evolution. This serene sameness, however, hides a far more turbulent story, one written in the faintest of imperfections. Yet within that profound and almost perfect smoothness, a whisper of imperfection tells the true story. If the cosmic microwave background were completely uniform, our universe would be a vast, empty, and eternal sea of featureless gas. We would not exist. The key to everything, from the grandest galaxy to the planet you live on, lies in the map of tiny temperature differences. These minute fluctuations, these wrinkles in the fabric of space-time, are the blueprints for all cosmic structure. Imagine the early universe as a calm pond, and these fluctuations are the ripples that eventually grew over billions of years into the islands of stars we call galaxies. They are the gravitational seeds around which all matter would eventually gather. Missions like the Planck Space Observatory have mapped these ancient wrinkles with breathtaking precision, painting a detailed picture of the infant cosmos. This map is not just a temperature chart, it is a cosmic recipe book. By reading the specific patterns of these hot and cold spots, scientists could deduce the fundamental ingredients of our universe. The data revealed that ordinary matter, the stuff that makes up you, me, and every star we see, constitutes less than 5% of the cosmic total. The rest is a mysterious mix of dark matter and dark energy. The geometry of the universe itself was also written into this pattern, confirming that on the largest scales, the cosmos is flat, a crucial detail that shapes its ultimate fate. These faint, billion-year-old imperfections are the reason we are here to observe them at all. They are the ultimate origin of structure, the initial conditions for the grand cosmic narrative that led to us. But what created these crucial wrinkles in the first place? This perfect uniformity presents one of the greatest puzzles in all of science, known as the horizon problem. Think of two people standing on opposite horizons of the Earth. They cannot see each other, and they have never met to exchange a single word, yet somehow they are both wearing identical outfits, down to the same color shirt and the same style of shoes. This is the fundamental strangeness we face with the cosmic microwave background. Regions of space that are now billions of light years apart on opposite sides of the observable universe share the exact same temperature. According to the standard Big Bang model, these regions were never in contact. Since nothing can travel faster than light, there simply has not been enough time since the beginning of everything for heat or energy to flow between these distant horizons and even out their temperature. They are cosmic strangers who have never shaken hands, yet they share an identical thermal signature. This is not just a minor detail. It is a direct challenge to our basic understanding of cause and effect. How could these separate parts of the cosmos have coordinated so perfectly without ever communicating? This impossible sameness is one of the strongest clues that our standard story of the universe's first moments is missing a crucial chapter, a dramatic event that connected these distant horizons before they were torn apart. The solution to this cosmic coordination problem is as radical as the problem itself. To explain how these distant regions could have once been in contact, physicists propose a breathtaking event called cosmic inflation. This was not a slow, steady expansion, but a violent, exponential growth spurt that occurred in the universe's very first moments. In a span of time almost too short to conceive, a fraction of a second so tiny it defies human intuition, the fabric of space itself stretched faster than the speed of light. Think of taking a single, microscopic patch of the newborn universe and inflating it to a size larger than our entire observable cosmos in less than the blink of an eye. This incredible idea resolves the horizon problem perfectly. Before inflation, that tiny patch was small enough for every part of it to communicate, to exchange energy and reach a uniform temperature. Then inflation blew it up to an immense scale, locking that perfect smoothness into place across vast distances. The regions we now see as opposite horizons were once cozy neighbors, and that is why they wear the same thermal outfit. But inflation did more than just iron out the cosmos. This hyper-stretching of space-time would have magnified the tiniest quantum jitters, the minuscule fluctuations that are a fundamental part of reality at the smallest scales. It took these microscopic whispers and stretched them into macroscopic ripples, planting the very seeds of structure that would later become the galaxies and the cosmic microwave background fluctuations we observe. The very process that created a smooth universe also, paradoxically, created the blueprint for all the lumpiness that followed. This violent stretching of space-time should have created ripples in the very fabric of the cosmos, distortions known as primordial gravitational waves. Think of the universe as a vast, calm lake. Inflation would have been like a tremendous pebble dropped into its center, sending powerful waves coursing through the water. These are not waves of light or matter, but waves of space and time itself, alternately stretching and compressing the distances between points as they pass by. According to the theory of inflation, this cosmic tremor should have left a permanent, if incredibly faint, imprint on the oldest light we can see, the cosmic microwave background. The specific signature to look for is a distinctive pattern in the light's polarization, a curl known as B modes. Finding this twisted fingerprint in the ancient glow would be the ultimate smoking gun, the direct evidence that inflation truly happened. The hunt for this signal has become one of the most intense and demanding quests in all of modern science. Teams of researchers use incredibly sensitive telescopes stationed at the South Pole and high in the Chilean deserts, places with exceptionally dry and stable air, to stare at the cosmic microwave background and search for this faint curl. They are looking for a distortion 1,000,000 times fainter than the temperature fluctuations we have already mapped. The challenge is monumental, as the signal can be easily mimicked or drowned out by foreground dust within our own galaxy. So far, this primordial whisper has remained elusive, hidden within the noise. Yet the search continues with ever more advanced technology, because the prize is the ultimate confirmation of our universe's most dramatic moment. To detect these waves would be to hear the echo of inflation itself, a direct message from the first fraction of a second of time. While we search for the echoes of inflation, another clue from the early universe is written in the very atoms that make up our bodies. In its first few minutes, the entire cosmos was a fleeting, spectacular nuclear furnace. This was the era of Big Bang nucleosynthesis, the process that forged the first atomic nuclei from a seething soup of fundamental particles. As the universe expanded and cooled from its initial unimaginable heat, protons and neutrons began to combine, but they only had a narrow window of time. For roughly the first 3 minutes, conditions were just right for nuclear fusion to occur everywhere at once. This was not fusion in stars, but a cosmic-wide event that created the primordial ingredients for everything to come. Then, as the universe continued to cool and thin out, this frantic nuclear activity slammed to a halt, freezing the elemental abundances in place. The predictions from this brief cosmic cook-off are incredibly precise. According to the theory, about 75% of the ordinary mass in the universe should be hydrogen, and nearly 25% should be helium. Trace amounts of heavier isotopes like deuterium, a heavy form of hydrogen, and lithium should also be left behind. These are not rough estimates, but exact percentages calculated from the known laws of physics applied to the universe's first moments. The stunning part is that when we look out at the oldest, most pristine corners of the cosmos, at gas clouds that have never been inside a star, we see these exact ratios. The observed abundance of hydrogen, helium, deuterium, and lithium matches the Big Bang prediction with breathtaking accuracy. This is not a coincidence. It is a direct quantitative test passed with flying colors. Think of it as a cosmic recipe that was written during the universe's infancy, a recipe we can still read today in the light from distant quasars and the composition of ancient stars. This perfect agreement is one of the strongest pillars supporting our entire modern cosmological story. It tells us that our understanding of physics can be trusted all the way back to when the universe was just a few minutes old, a profound validation of our quest to decipher the cosmos. Yet this triumphant success story holds one glaring and persistent crack, a single prediction that stubbornly refuses to match our observations. This is the lithium problem. While the amounts of hydrogen, helium, and deuterium line up perfectly with the cosmic recipe, the seventh element on the periodic table is a dramatic outlier. The models for Big Bang nucleosynthesis predict a specific trace amount of lithium-7, the most common isotope of this light metal, should have been forged in the first 3 minutes. But when we look at the atmospheres of the most ancient stars in our galaxy, stars that formed from that pristine primordial gas, we find only about 1/3 of the expected lithium. The universe seems to be missing a huge portion of this fundamental element. How could the calculations be so spectacularly right for 3 ingredients and so definitively wrong for the 4th? This is not a small discrepancy. It is a factor of 3, a huge gap that has resisted explanation for decades. The hunt for this missing lithium has led scientists down 2 very different paths. One possibility points to our understanding of the stars themselves. Perhaps these ancient stars have internal processes that slowly destroy lithium over their immensely long lifetimes, dragging the original surface abundance down. Another, more radical idea is that our knowledge of the nuclear physics involved is incomplete. Maybe unknown particles, like certain types of dark matter, interacted with the primordial nuclei and destroyed some of the lithium after it formed, altering the frozen record. Or perhaps there is a flaw in how we model the turbulent conditions of that first nuclear furnace. This small anomaly serves as a vital reminder that even our most successful theories are not complete. The lithium problem is a tiny, stubborn clue that the early universe might still hold secrets about its own fundamental laws. secrets that could point toward physics we have not yet discovered. While we grapple with the missing lithium, an even deeper mystery defines the cosmos, a ghost that shaped the universe from its very first moments. This is the enigma of dark matter. All the stars, planets, and galaxies we see with every telescope are just the visible froth on a vast, hidden ocean. This mysterious substance makes up roughly 85% of all the matter in the universe, yet it remains utterly invisible. We cannot see it because it does not emit, absorb, or reflect any light. Its presence is revealed only through its immense gravitational pull. The first compelling clue came from the way galaxies spin. When astronomers measured the speeds of stars orbiting within spiral galaxies, they found something astonishing. According to the laws of gravity, stars on the outer edges of a galaxy should move much more slowly than those near the center, just as Pluto orbits our Sun more slowly than Earth. But the data showed the opposite. Stars far from the galactic center whip around at nearly the same high speed as those closer in. The only way this makes sense is if the entire galaxy is embedded within an enormous, invisible sphere of matter, a dark matter halo whose gravity grips the speeding stars and keeps them from flying away. This unseen anchor is the cosmic glue holding fast-rotating galaxies together. Another dramatic effect is gravitational lensing. Einstein predicted that massive objects warp the fabric of space-time, bending the path of light that travels past them. Dark matter, with its tremendous mass, acts as a cosmic lens. When we look at distant galaxies, we sometimes see their light stretched and distorted into strange arcs and multiple images. This happens because the light is bending around an immense, invisible concentration of dark matter lying between us and the source. It is like looking through a rippled glass window at a distant street lamp and seeing its shape twisted and smeared. By mapping these distortions, we can literally chart the distribution of this unseen material. Most profoundly, dark matter was the essential architect of the cosmic web. The tiny wrinkles in the early universe, the ones imprinted on the cosmic microwave background, were far too weak for gravity alone to sculpt into galaxies within the age of the universe. Dark matter provided the extra gravitational muscle. Because it does not interact with light, it was free to begin clumping together long before normal matter could, forming vast invisible scaffolds. Ordinary atoms then simply flowed into these gravitational wells where they could cool, condense, and eventually ignite as the first stars and galaxies. The entire large-scale structure of the modern universe, with its great filaments of galaxies surrounding immense voids, is a perfect cast of an underlying dark matter skeleton. We see its ghostly hand in the spin of galaxies, the bending of light, and the very blueprint of creation. Yet after decades of searching, we still have no idea what it is made of. It is not any known particle. This invisible substance that dominates the cosmos, that dictated our very existence, remains one of the most profound and humbling mysteries in all of science. Just as we began to map the shadowy architecture of dark matter, an even more baffling discovery shattered our cosmic expectations. For much of the 20th century, astronomers believed the universe's expansion was gradually slowing down, a natural coasting after the initial explosive force of the Big Bang. The collective gravity of all the matter in the cosmos, both seen and unseen, was thought to be acting as a cosmic brake, gently pulling everything back together. This was the prevailing view, a logical conclusion drawn from the laws of physics as we understood them. Then, in the late 1990s, two independent teams set out to measure this deceleration by observing incredibly distant stellar explosions known as Type 1, a supernova. These supernovae are crucial because they act as standard candles, meaning they all explode with roughly the same intrinsic brightness. By carefully measuring how bright they appear from Earth, astronomers can calculate their precise distance. Furthermore, by analyzing the color of their light, which stretches as the universe expands, they can determine how much the universe has stretched since the explosion occurred. The researchers were looking for confirmation that the most distant supernova, whose light had been traveling for billions of years, showed signs of a universe expanding faster in the past, evidence of that expected slowdown. What they found was the exact opposite. The data revealed that the most distant supernova were fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was actively pushing the cosmos apart, overpowering the relentless pull of gravity. This discovery was so shocking and counterintuitive that the team spent years checking and rechecking their work for errors. There were none. The universe's expansion is accelerating. This baffling phenomenon was given a simple yet profound name: dark energy. When we tally up the entire energy budget of the cosmos, this unknown force is the dominant component, making up a staggering 68% of everything that exists. Dark matter constitutes about 27%, and all the ordinary matter, every star, planet, and galaxy we can see, amounts to less than 5%. We live in a universe dominated by two invisible, mysterious entities we do not understand. So what could this repulsive energy be? The leading and most conservative idea is that it is a property of space itself. Empty space is not truly empty according to quantum physics, but seethes with virtual particles that constantly pop in and out of existence. This vacuum energy could exert a negative pressure, a kind of cosmic anti-gravity that drives galaxies apart. The problem is that when theorists calculate the predicted strength of this vacuum energy, the result is wrong by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros, the single worst prediction in the entire history of physics. Other theories suggest dark energy could be a dynamic field that permeates the cosmos, one that could change over time. Its implications for the ultimate fate of the cosmos are profound. If dark energy remains constant, the acceleration will continue forever. In a future trillions of years from now, the expansion will become so rapid that distant galaxies will be pushed beyond our cosmic horizon, their light forever lost to us. The observable universe will shrink to our local group of gravitationally bound galaxies, leaving the rest of space an eternal, expanding blackness. If dark energy grows stronger, it could lead to a terrifying scenario known as the Big Rip, where the fabric of space-time itself is torn apart, shredding galaxies, stars, planets, and even atoms. This mysterious force, discovered only decades ago, now holds the key to the final chapter of our universe's story. Zoom out far enough, and the universe reveals its true architecture, a structure so vast it defies simple description. This is the cosmic web, the largest pattern known to exist. Galaxies are not scattered randomly through the void like lonely islands. Instead, they cluster into immense walls and long, delicate filaments, weaving a tapestry on a billion light-year scale. These brilliant strands of stars and galaxies surround and separate colossal, nearly empty regions known as cosmic voids, dark abysses of space that can span hundreds of millions of light-years across. The overall impression is that of a cosmic sponge, or a network of interconnected neurons with galaxies tracing the dense walls and filaments. This grand design did not appear by chance. Its blueprint was encoded in the earliest moments of the cosmos, within those tiny temperature wrinkles we see in the cosmic microwave background. Those minute variations in density, those seeds of future structure, were the starting points. Over billions of years, gravity acted as a relentless sculptor. Regions that were slightly denser than average had a stronger gravitational pull, drawing in more and more matter from their surroundings. Dark matter, with its powerful gravity and its inability to interact with light, led the way, forming an invisible skeleton first. Ordinary matter then flowed into this pre-existing scaffold, condensing along the dark matter filaments and igniting into the first stars and galaxies. The vast voids are the other side of this process, the regions that were initially slightly less dense and were gradually emptied out as matter flowed toward the growing nodes of the web. By meticulously mapping the positions of millions of galaxies, projects like the Sloan Digital Sky Survey have given us a three-dimensional chart of this cosmic architecture. This map is more than just a pretty picture, it is a forensic tool. The specific way the web is woven, the thickness of its filaments and the sizes of its voids depends critically on the properties of dark matter. A fast-moving, hot dark matter particle would smooth out small-scale structures, while a slow-moving, cold dark matter particle allows for the intricate, clumpy web we actually observe. The data strongly favors cold dark matter, helping us narrow down what this mysterious substance could be. Furthermore, the web's structure is a direct echo of the initial conditions from inflation. The pattern of the wrinkles in the cosmic microwave background perfectly predicts the pattern of the cosmic web we see today. It is a stunning confirmation that we are reading the universe's history correctly, from its first quantum tremors to the grand, glittering metropolises of galaxies we observe now. Deep within the cosmic dark ages, a solitary light finally flickered on. This was the moment of first dawn, ignited by the very first stars in the universe. Astronomers call these legendary and still hypothetical objects population 3 stars. They were unlike any sun we see today, composed of nothing but the 2 simplest elements, pristine hydrogen and primordial helium. There were no planets like Earth orbiting them, for there was no silicon, no oxygen, no carbon, no iron. The universe was far too young for the complex elements that form rocks and life. These stellar titans were born from the pure gravitational collapse of those initial density wrinkles imprinted by inflation. Without heavier elements to help the gas clouds cool and fragment, the first stars could grow to immense sizes, potentially hundreds of times more massive than our own sun. Imagine a single star shining with the fury of millions of our suns, a brilliant, short-lived beacon in an otherwise unbroken night. Their sheer mass dictated a ferocious and fleeting existence. They burned at extreme temperatures, living fast and dying young in colossal supernova explosions that would, for the first time, seed the cosmos with the heavier elements we are made of. But their most profound impact on the cosmos was the light they emitted. Their intense, searing ultraviolet radiation began to tear apart the surrounding fog of neutral hydrogen gas that filled the entire universe. This marked the beginning of the epoch of reionization, a pivotal cosmic transformation. Think of the early universe as a room filled with a dense, opaque mist. The first stars were like the first lamps switched on, their powerful light slowly burning away the fog, making the room transparent. This process did not happen everywhere at once, but gradually, as more and more stars ignited, creating expanding bubbles of clear, ionized gas within the neutral hydrogen. These bubbles grew and overlapped over hundreds of millions of years, eventually rendering the entire intergalactic medium transparent to ultraviolet light, a state it has remained in ever since. We are now on the cusp of directly witnessing this cosmic dawn. The James Webb Space Telescope, with its unprecedented infrared vision, is peering back in time, searching for the faint glow of those first galaxies and the population 3 stars that powered them. It is looking for the specific signature of their light as it began to carve out those first transparent bubbles in the cosmic fog. Finding direct evidence of these first stars would be like discovering the original pioneers who first lit the lamps of the cosmos, ending the universe's dark ages and setting the stage for everything that was to come. This crucial transition, the epoch of reionization, was the universe's final great metamorphosis. For hundreds of millions of years after the first stars ignited, the cosmos remained a patchwork of light and shadow. Those brilliant early stars and the first quasars, the unimaginably bright cores of nascent galaxies, acted as cosmic lighthouses. Their intense ultraviolet radiation blasted out into the surrounding fog of neutral hydrogen, a gas that efficiently absorbs such high-energy light. But this radiation was so powerful that it could rip electrons away from the hydrogen atoms, turning them into a transparent, ionized plasma. Think of it as a vast landscape shrouded in a deep, persistent frost. The first stars were like the sun rising on a cold morning, each one creating a small, clear puddle of meltwater around itself. As more and more stars and quasars flickered on, these puddles of transparent space grew larger and began to merge. Over time, the entire frosty blanket evaporated, leaving the universe clear and open to the passage of light, a state it has maintained for billions of years since. Observing this specific era is one of the greatest challenges in modern astronomy. We cannot see the process directly because the very same neutral hydrogen fog that was being burned away blocks our view. The light from those first luminous objects is absorbed before it can ever reach us. So how do we study an event we cannot directly witness? Astronomers use a clever trick, employing the most brilliant beacons in the distant universe as cosmic backlights. Quasars, with their phenomenal luminosity, are perfect for this. As their light travels for billions of years on its journey to our telescopes, it passes through the remnants of that reionizing fog. The neutral hydrogen atoms along the path imprint a distinctive signature on the quasar spectrum, a thicket of absorption lines known as the Lyman alpha forest. By carefully analyzing this forest of lines, scientists can determine when the hydrogen fog finally cleared. It is like studying a distant street lamp through a fading fog. You cannot see the fog itself directly, but by observing how the lamp's light is dimmed and reddened, you can map the fog's density and know the precise moment it finally dissipates. This forensic analysis of ancient light tells us that reionization was a drawn-out process, likely completed by the time the universe was around 1 billion years old, finally setting the cosmic stage for the clear and structured universe we observe today. This ancient light holds the ultimate portrait of cosmic infancy. When we observe the cosmic microwave background, we are peering back to a moment just 380,000 years after the Big Bang. That may sound like a long time, but on the cosmic scale, it is the universe's very first breath. At that pivotal instant, the entire cosmos transformed from an opaque, searing plasma into a transparent, expanding gas. Before this moment, the universe was a roiling fog of charged particles where light was constantly scattered, trapped in a chaotic dance with matter. The moment it cooled enough for electrons to combine with protons and form the first neutral atoms, the fog instantly lifted. The light, once trapped, was suddenly set free, and it has been traveling across the void ever since, carrying a pristine snapshot of that exact transition. This is the oldest image we can ever capture, a time before the first star ever flickered, before the first galaxy ever swirled into existence. What we see is not a tapestry of brilliant suns, but a subtle map of temperature and density, the foundational blueprint for everything to come. Every slight variation, every hot and cold spot in that glow, is a direct message from the primordial universe. It tells us about the initial conditions, the geometry of space, and the very ingredients that would later cook up galaxies, planets, and life itself. This is not merely a fossil, it is a living, breathing document, a time capsule whose contents we are only just beginning to fully decode. This profound flatness is etched into the ancient light itself. The cosmic microwave background reveals that our universe, on the largest imaginable scales, is geometrically flat. This is not flat like a tabletop, but a statement about the fundamental geometry of space-time itself. In a flat universe, the rules of geometry we learned in school hold true. Two parallel laser beams fired across the void will remain perfectly parallel for all eternity, never converging or diverging. This specific condition depends on the universe having a precise, critical density of matter and energy. Think of this critical density as a cosmic balancing point. If the universe had been denser at its birth, its gravity would have caused space to curve back on itself into a closed sphere like the surface of a balloon. In that reality, parallel lines would eventually meet. If the density had been lower, space would be curved outward in an open, saddle-like shape, and those same beams would steadily drift apart. The fact that we observe a flat universe means the actual density is, and always has been, extraordinarily close to that perfect critical value. This is deeply peculiar. For the universe to be so perfectly balanced today, its initial density must have been fine-tuned to an almost impossible degree of precision at 1 second after the Big Bang, accurate to within 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. The odds of this happening by chance are so astronomically low that it points toward a physical mechanism that forced the universe into this flat state. This is where cosmic inflation provides the elegant answer. That violent, hyper-fast stretching of space in the first instance would have acted like a cosmic iron, relentlessly smoothing out any initial curvature. No matter what shape the universe was born with, inflating it to such an immense size would make it appear flat to any observer within it, just as a small patch of a giant balloon feels flat to an ant crawling on its surface. The observed flatness is not a lucky coincidence, but a direct prediction and a powerful piece of corroborating evidence for the inflationary paradigm. It tells us that the universe we can see is just a tiny, flat fragment of a far grander and possibly curved whole. Frozen into the very distribution of the galaxies we see today is a cosmic echo, a fossilized sound wave from the universe's fiery youth. This is the clue of Barrian acoustic oscillations. In that searing plasma of the early universe before atoms could form, matter and light were locked in a tight embrace. Photons exerted immense pressure, creating a powerful outward force against the inward pull of gravity. This tug-of-war generated sound waves, massive ripples that propagated through the primordial soup. Think of the entire observable universe as a single, unimaginably vast bell, ringing with a deep, resonant tone. These pressure waves traveled outwards from every slight over density, pushing a spherical shell of matter ahead of them, much like a sound wave pushes air. For nearly 400,000 years, these waves expanded through the hot plasma. Then, in an instant, everything changed. When the universe cooled enough for atoms to form and the cosmic microwave background was set free, the music suddenly stopped. The plasma vanished, and with it, the pressure from the photons. The sound waves froze in their tracks, halting their expansion and leaving behind a lasting imprint. Each of those original overdensities was left surrounded by a single, characteristic spherical shell of matter, a fossilized bubble with a very specific radius. This radius became a permanent standard ruler etched into the cosmos. Today, when we map the positions of millions of galaxies, we do not see a random scatter. We see that these galaxies have a subtle preference to be separated by a specific distance, a scale of about 500 million light-years. This is the size of that frozen sound wave, stretched to an immense scale by the expansion of the universe over billions of years. It is as if we found that all the cities on Earth were consistently spaced exactly 1,000 miles apart, a pattern that could only point to a single, coordinated origin event. Scientists now use this standard ruler to take the universe's vital signs. By measuring this exact scale at different cosmic epochs, at different distances from us, they can chart how the expansion rate of the universe has changed over time. It becomes a direct probe for the influence of dark energy. Does the ruler's apparent size change with time in a way that matches a constant dark energy, or does it suggest something more dynamic? This ancient sonic fossil, imprinted when the universe was a fraction of its current age, provides one of our most powerful and reliable tools for understanding the mysterious force that now governs our cosmic fate. Even as we mapped the cosmic web, a simple inventory of the universe revealed something was misplaced. We knew precisely how much ordinary matter should exist, a number calculated from the Big Bang's own nuclear recipe and confirmed by the cosmic microwave background. Yet for decades, when astronomers added up all the visible matter in stars, galaxies, and the cool gas we could easily detect, nearly half of it was simply gone. This was the missing baryons problem. Baryons are simply the particles that make up the familiar world, protons and neutrons, the stuff of planets and people. The cosmos had apparently lost half of its normal material. The solution was as elusive as it was elegant. Theorists predicted this missing matter was not in bright, dense objects, but spread throughout the vast, empty corridors between galaxies in a form known as the warm-hot intergalactic medium, or WIM. Imagine a gigantic, invisible atmospheric ocean filling the cosmic voids, a sparse gas so hot it glows only in faint X-rays, and so diffuse that a cubic meter of it might contain only a few atoms. Spotting this ghostly web has been one of astronomy's greatest technical challenges. It is like trying to see the heat haze rising from a single, distant sidewalk on a summer day. To find it, scientists turn to brilliant cosmic lighthouses known as quasars. As the light from a quasar travels for billions of years to reach us, it passes through these invisible filaments of the WIM. Specific elements within that hot gas, like highly ionized oxygen, absorb very particular wavelengths of the quasar's light. This imprints a unique barcode of absorption lines onto the quasar's spectrum. By analyzing this barcode with powerful X-ray telescopes, astronomers can not only detect the WIM presence but also measure its temperature, density, and distribution. Recent observations have finally begun to close the cosmic budget, finding these vast reservoirs of hot gas exactly where the models of the cosmic web predicted they would be. The missing matter was hiding in plain sight all along, woven into the very fabric of space itself, completing the inventory of the ordinary universe and confirming our deepest theories of cosmic structure. A crack has appeared in our most fundamental picture of the cosmos. For years, we have measured the universe's current rate of expansion, a number called the Hubble constant, using two very different kinds of cosmic rulers. The first method looks at the nearby universe using pulsating stars known as Cepheids variables and the brilliant flash of type 1, a supernova. These are our local speedometers, giving us a direct reading of how fast galaxies are moving away from us right now. The second method uses the cosmic microwave background as a starting point. By meticulously analyzing the patterns in that ancient light, we can run the cosmic film backward to understand the initial conditions, then forward using our established laws of physics to predict what the expansion rate should be today. These two methods, one observing the present and one deducing the present from the deep past, should arrive at the exact same number, but they do not. The universe, as measured by its ancient echo, is expanding significantly slower than the universe we see around us today. This discrepancy is not a small, negligible error. It is a persistent and growing tension that has withstood over a decade of intense scrutiny and improved measurements. Scientists have checked and rechecked for possible errors, for hidden dust, for any systematic flaw in their observations. The tension remains stubborn and unresolved. This is not just a minor accounting problem. It suggests that the cosmic rulebook we have been using, the entire standard model of cosmology that beautifully explains so much, might be subtly wrong. Perhaps dark energy is not constant but is evolving, growing stronger over time. Or maybe dark matter possesses properties we have not yet imagined, allowing it to interact in new ways. Some theorists even speculate that we are seeing the first evidence for a new type of fundamental particle or field that faded from importance long ago but has left its mark on the expansion history. The Hubble tension is a modern cosmic crisis, a direct challenge that tells us our map of the universe, for all its incredible detail, is still missing a crucial feature. The most exciting possibility is that this is not a flaw in our observations, but a glimpse of the new physics waiting to be discovered. This staggering failure of prediction is known as the cosmological constant problem, and it represents the single greatest mismatch between theory and observation in all of science. Our most trusted laws of physics, when applied to the vacuum of space, produce a number for the energy density of nothingness that is catastrophically wrong. It is incorrect by a factor of 10 to the power of 120. To grasp the sheer scale of this error, consider that the entire observable universe contains roughly 10 to the power of 80 atoms. This discrepancy is a 1 followed by 120 zeros, a number so inconceivably vast it dwarfs the count of every particle in the cosmos. According to our best quantum theories, empty space is not truly empty. It is a seething, bubbling foam where virtual particles constantly flicker in and out of existence. This quantum jitter should endow every tiny cubic centimeter of vacuum with a tremendous amount of energy, a violent background hum that would exert a powerful repulsive force. If this theoretical calculation were correct, this vacuum energy would have ripped the universe apart in its first instant, preventing any galaxy, star, or planet from ever forming. Yet we observe a universe that has lasted for billions of years, with structures that have had time to evolve. The dark energy we actually measure is there, but it is mind-bogglingly weaker, a faint whisper of a force compared to the theoretical roar. This is not a minor adjustment. It means we are fundamentally missing something. The cosmological constant problem is a screaming clue that our understanding of gravity, as described by Einstein's general relativity, and our understanding of the quantum world are incompatible. They cannot both be right in their current forms when applied to the vacuum. Solving this would require a theory of quantum gravity, a framework that unites the very large with the very small, a challenge that has eluded physicists for a century. This is not just a mathematical puzzle, it is a direct message from the universe that our most profound theories are incomplete, and that the true nature of nothingness is one of the ultimate mysteries. Our very existence is a profound cosmic puzzle. Every single thing we see, from the stars above to the ground beneath our feet, is made of matter, but the laws of physics present us with a stunning contradiction. In the immense energy of the Big Bang, energy should have condensed into perfectly equal amounts of matter and antimatter. For every proton created, an antiproton should have sprung into being. For every electron, a positron. These particles are identical to their matter counterparts in mass, but they carry the opposite electrical charge. The problem is, when matter and antimatter meet, they annihilate each other in a flash of pure energy. If the universe had been born with perfect symmetry, all the particles should have found their antimatter twins, and the entire cosmos would have dissolved back into a sea of radiation, leaving behind absolutely nothing. There would be no atoms, no chemistry, no planets, and no one to wonder about at all. The fact that we are here in a universe filled with galaxies and gas and life means this perfect cancellation did not happen. A tiny, almost imperceptible imbalance must have tipped the scales. One extra particle of matter was left over for every billion annihilations. From that 1 in a billion survivor, from that faintest ghost of an asymmetry, our entire universe was built. Physicists call the process that created this bias baryogenesis, the genesis of baryonic matter. It points to a fundamental crack in the mirror of nature, a set of conditions in the early universe where the laws of physics treated matter and antimatter slightly differently. Finding the source of this broken symmetry is one of the great quests of particle physics. It requires something beyond the standard model, a new set of rules that operated in the extreme heat of the first fractions of a second. Did some unknown particle decay favor matter over antimatter? Did the universe undergo a phase transition like water freezing into ice that segregated the two? The answer is written into every atom in our bodies, a silent testament to a moment when the cosmos chose one path over another, leaving the ghost of antimatter as a missing clue to our own origins. Rewind the cosmic clock to the first millionth of a second, and you would find a universe so alien it defies all intuition. This was a realm where the very concepts of protons and neutrons were meaningless, where the fundamental building blocks of matter were utterly unshackled. In that searing heat and pressure, the universe existed as a quark-gluon plasma, a primordial soup where quarks and the gluons that bind them roamed freely, unconfined by any atomic nucleus. It was a perfect, scalding liquid, the hottest and densest state of matter ever to exist. For a fleeting instant, the cosmos was not a collection of solid things, but a single, unified fluid of pure energy and potential. To understand this state is to witness the moment matter itself was forged. We are not merely reading about this in a textbook, we are recreating it. Inside the world's most powerful particle accelerators, like the Large Hadron Collider, scientists slam atomic nuclei together at nearly the speed of light. These collisions concentrate an immense amount of energy into a tiny, microscopic point, briefly generating temperatures over 100,000 times hotter than the core of the Sun. For a sliver of a second, the protons and neutrons in those nuclei melt, their constituent quarks and gluons bursting free to form a fireball of quark-gluon plasma no wider than an atomic nucleus. Then, just as quickly, this droplet of the early universe expands and cools, and the quarks snap back into confinement, forming a shower of new, familiar particles that we can detect. By analyzing this particle shrapnel, we can study the properties of that primordial fluid. We have learned it is not a gas, but a liquid with virtually zero friction, a perfect superfluid that flows without viscosity. This is the state from which all atomic matter later condensed, the cosmic cauldron where the first protons and neutrons were cast. We are literally looking into the pot from which our own substance was poured. Even the most energetic particles in the universe must obey the cosmic speed limit, a rule that seems to have been broken. From the depths of space, atomic nuclei travel at nearly the speed of light, carrying energies so immense they are millions of times more powerful than anything we can produce in our largest particle colliders. These are ultra-high-energy cosmic rays, and their very existence presents a staggering puzzle. According to a prediction made by physicists Greisen, Zatsepin, and Kuzmin, there should be a firm ceiling on their energy, a point now known as the GZK cutoff. The reasoning is simple yet profound. The universe is not empty, it is filled with the faint afterglow of creation, the cosmic microwave background. For a proton or an atomic nucleus traveling at such fantastic speeds across millions of light years, this background radiation is no longer a harmless whisper. Each microwave photon is blue-shifted into a barrage of gamma rays, like driving into a relentless storm of high-energy bullets. The collisions between these cosmic ray particles and the background photons should sap their energy, tearing them apart over long distances. No particle from a distant galaxy should be able to reach Earth with an energy beyond this cutoff, yet our detectors have recorded them. We have seen these cosmic cannonballs, and their origin is a complete mystery. The fact that they arrive at all suggests two equally thrilling possibilities. Perhaps their sources are unexpectedly close within our own local cosmic neighborhood, born from cataclysms we have yet to identify. Or more radically, their journey hints at exotic new physics. Maybe these particles are not protons at all, but something stranger, a form of matter that does not interact with the background radiation in the same way. They could be the decay products of hypothetical super-heavy dark matter particles, or their paths could be subtly altered by dimensions of space-time we cannot perceive. Each detection is a message from the void, a clue written in a language of impossible energy that challenges our understanding of the cosmos on both its largest and smallest scales. Another secret of the early cosmos is hidden within a phantom forest. When we point our most powerful telescopes at the brilliant hearts of distant quasars, we capture more than just their intense light, we capture a ghostly silhouette. The quasar's light, after traveling for billions of years, carries an intricate barcode of thousands of dark absorption lines, a dense thicket known as the Lyman alpha forest. Each one of these lines is a cosmic footprint. They are created when the quasar's light passes through immense, diffuse clouds of neutral hydrogen gas that float in the vast emptiness between galaxies. Every single line corresponds to a different cloud at a different distance, and thus a different moment in the universe's history. The light from the most distant clouds is stretched the most, its absorption line shifted far toward the red end of the spectrum. Light from nearer clouds is less stretched. This creates a sprawling forest of lines across the spectrum, a direct record of the universe's evolving structure. This forest is not a static picture, it is a living fossil, a timeline of cosmic gas stretching from the present day all the way back to the epoch of reionization. By meticulously counting the trees in this forest and analyzing their spacing, astronomers can reconstruct the distribution of this primordial hydrogen. They can see how the gas was arranged when the universe was half its current age, a quarter of its age, and so on. The density of the lines tells us about the clumpiness of the early universe, revealing the invisible gravitational wells of dark matter that were already pulling matter together. Furthermore, the width and shape of each absorption line act as a cosmic thermometer. A broad, fuzzy line suggests the hydrogen cloud is hot and its atoms are moving rapidly, while a sharp, narrow line indicates a cooler, more placid cloud. This allows scientists to map the temperature of the intergalactic medium across billions of years, watching it heat and cool as energy from stars and quasars poured into it. The Lyman alpha forest is therefore one of our richest archives, a natural spectrometer written across the sky that lets us read the detailed history of the universe's most abundant element, tracing its journey from a uniform fog to the raw material for galaxies. Galaxies themselves carry the scars of ancient cosmic battles, and their very shapes tell a story of violent transformation. Look at a modern galaxy cluster, a dense metropolis of thousands of galaxies, and you will find it dominated by elliptical galaxies. These are vast, amorphous swarms of old, red stars, like retired giants that have long since burned through their fuel for new star birth. They are quiet, peaceful, and largely inert. But this was not always the case. In the 1980s, astronomers Beatrice Tinsley and Alan Omler made a startling discovery. When they looked at very distant clusters whose light has been traveling for billions of years to reach us, they saw a completely different picture. Those ancient clusters were teeming with spiral galaxies, beautiful disk-shaped systems alive with the blue light of young, hot stars and active star formation. The Butcher-Omler effect reveals a universe in flux, showing that the proportion of these vibrant, spiral galaxies drops dramatically as we look closer to the present day. The distant, younger universe was a far more lively and fertile place. So what force transformed these bustling spiral cities into quiet, elliptical retirement homes? The culprit is the incredibly dense environment of the cluster itself. A galaxy cluster is a gravitational prison, with members whipping past one another at speeds of millions of miles per hour. In this chaotic environment, galaxies rarely collide head-on, but they undergo a process called galaxy harassment. They experience rapid, repeated gravitational tugs from their neighbors as they pass by. These interactions are like 1,000 small thefts, stripping away a galaxy's delicate reservoir of cold gas, the very raw material needed to form new stars. Without this gas, the spiral galaxy cannot sustain its star-forming factories, and its characteristic disk structure is disrupted and puffed up. In more extreme cases, galaxies do merge, their gravitational fields pulling and twisting each other until their distinct shapes are completely erased, morphing into a single, featureless elliptical galaxy. The Butcher-Omler effect is a direct snapshot of this cosmic evolution in action. It shows us that a galaxy's fate is not sealed at birth, but is profoundly shaped by its social life. A galaxy that lives a quiet, isolated existence in a cosmic suburb might retain its beautiful spiral structure for eons, but a galaxy that moves into a dense urban cluster is destined to have its gas stripped away, its star formation quenched, and its identity fundamentally altered. This is the slow, gravitational drama that has been playing out over billions of years, turning the vibrant clusters of the early universe into the red and dead metropolises we see today. Even the steady glow of distant galaxies carries a coded message about cosmic history. We can measure not just a galaxy's total light, but also its surface brightness, how much light arrives from a given patch of its apparent size in the sky. A simple, intuitive idea from physicist Richard Tolman predicted how this should behave over cosmic distances. In a static, non-expanding universe, the surface brightness of a galaxy should remain constant, no matter how far away it is. Think of a street lamp. As you walk away from it, it appears fainter overall, but the brightness of its surface, the bulb itself, does not actually change. The light is simply spread out. Now, imagine that the very space between you and the lamp is also stretching. This changes everything. In an expanding universe, the light from a distant galaxy is not only spread thinner by distance, but each individual photon of light is also stretched to a longer, redder wavelength, losing energy in the process. This double whammy of effects means that a galaxy's surface brightness should fade much faster with distance than it would in a static cosmos. It dims not just because of the inverse square law, but because the expansion of space itself robs the light of its energy. When astronomers perform this test, that is precisely what they observe. The most distant galaxies are dramatically dimmer per unit area than their closer counterparts, a dimming that aligns perfectly with an expanding universe and definitively rules out a steady, unchanging cosmos. This quiet, persistent dimming across the gulf of space is a powerful, independent confirmation that we live in a dynamic, stretching universe, one that has been growing larger for billions of years. The ancient light of the cosmic microwave background is not just a static image, it is a dynamic screen, and its story changes when something gets in the way. A subtle but powerful clue comes from the Sunyaev-Zel'dovich effect, a phenomenon that turns the afterglow of the Big Bang into a cosmic searchlight. Imagine you are listening to a faint, constant hum from a distant radio station. Suddenly, a group of people walks between you and the antenna. They do not block the sound completely, but their bodies scatter the radio waves, slightly distorting the signal you receive. This is analogous to what happens on a cosmic scale. The cosmic microwave background radiation is that constant hum, filling all of space. When its photons travel for billions of years and pass through a massive galaxy cluster, they must push through the incredibly hot gas that is trapped by the cluster's immense gravity. This is not a cool, thin gas, but a superheated plasma, millions of degrees hot, filled with energetic electrons. As the cold, primordial photons from the early universe fly through this hot cloud, they collide with these fast-moving electrons. The electrons give the photons a slight kick, a tiny boost of energy. This process is called inverse Compton scattering. The result is a minute but detectable distortion in the cosmic microwave background at the precise location of that galaxy cluster. The overall number of photons does not change, but their energy does. The low-energy microwaves get shifted to slightly higher energies. When we look at our detailed map of the cosmic microwave background, this cluster location will appear as a tiny, faint cold spot. It is cold only in a relative sense because the specific low-energy microwaves we are looking for have been scattered away from that line of sight, leaving a slight dip in the signal. This is a revolutionary way to find the most massive structures in the universe. Traditional methods rely on seeing the light from the galaxies themselves, which becomes incredibly difficult at vast distances. The Sunyaev-Zel'dovich effect, however, works independently of distance. It does not matter if the cluster is 5 billion light-years away or 10 billion, the effect on the background radiation is the same. It depends only on the density and temperature of the hot gas in the cluster. This allows astronomers to conduct blind surveys, scanning the cosmic microwave background for these characteristic cold spots and discovering galaxy clusters we could never have seen with optical telescopes alone. By building catalogs of these clusters across cosmic time, we can trace the growth of the largest structures in the universe, testing our models of dark energy and gravity on the grandest possible scale. The echo of creation itself becomes the tool we use to map the universe's evolving architecture. The delicate spiral of a galaxy is a masterpiece of gravitational balance, but it is also surprisingly fragile. These vast, thin disks of stars and gas, like our own Milky Way, should not have survived the chaos of the cosmos unscathed. Over billions of years, the constant gravitational tugs from smaller satellite galaxies, the close flybys of galactic neighbors, and even the occasional full-scale merger should have acted like stones thrown into a still pond. Each interaction would send disruptive waves through the delicate disk, scattering stars into a thick, puffy halo and blurring that beautiful, orderly structure into a formless elliptical cloud. The fact that we see so many pristine spiral galaxies today, including our own, is a profound clue. It tells us that our local cosmic environment must have been unusually quiet for an immensely long time. While the early universe was a violent dance of colliding and merging galaxies, the era of frequent major mergers seems to have largely passed. Our Milky Way has likely avoided a catastrophic collision with another large galaxy for over 10 billion years, allowing its disk to settle, thin out, and maintain its iconic pinwheel shape. This galactic peace is only temporary, of course. In a few billion years, we are destined to merge with the Andromeda Galaxy, an event that will almost certainly destroy both spiral structures and forge a new, giant elliptical galaxy. For now, the very existence of our thin galactic disk is a silent testament to a long and surprisingly stable chapter in our cosmic history, a period of grace that allowed our solar system to form and life to emerge on a quiet spiral arm. Our own planet's history holds a cosmic contradiction. The Sun, a steady anchor in our sky, was once a far weaker star. Astrophysical models tell us with confidence that in its youth, our Sun burned about 30% fainter than it does today. This is a normal part of a star's life cycle as its core gradually grows denser and hotter. Apply that simple fact to the early Earth and a chilling prediction emerges. Under that fainter young sun, our planet should have been a global snowball, a frozen world locked in ice from pole to pole. The entire surface should have been a glittering wasteland, far too cold for liquid water to exist. Yet the geological record speaks with a different, warmer voice. We find ancient rocks shaped by flowing water, sedimentary layers that could only have been deposited in rivers and oceans dating back to that very same era. The evidence is undeniable. Liquid water flowed on Earth when, by all rights, it should have been frozen solid. This is the faint young sun paradox, a puzzle written in stone and starlight. The solution forces us to look beyond the sun and into the air itself. Our planet's early atmosphere was a vastly different place, likely much thicker and rich in powerful greenhouse gases like methane and carbon dioxide. This primordial blanket would have trapped the sun's meager heat with incredible efficiency, creating a natural planetary thermostat that kept the globe warm. It suggests a complex and dynamic interplay between a star's slow evolution and a planet's active geology and climate. A world is not just a passive rock orbiting a fire. It is a system where the atmosphere, the oceans, and even the earliest life forms themselves may have worked in concert to maintain a delicate, habitable balance against the cold of space. This paradox is not just about Earth's past, it is a crucial clue for our search for life elsewhere. It tells us that a star's current brightness is only one part of the equation for habitability. A planet's own character, the composition of its air and the activity of its interior, can rewrite the rules, turning a seemingly frozen orbit into a cradle for life. This profound silence from the cosmos may be the most important clue of all. We gaze out at a universe filled with hundreds of billions of galaxies, each home to hundreds of billions of stars, with countless planets orbiting in their habitable zones. The raw numbers suggest a cosmos teeming with potential, a galaxy that should be buzzing with the signals and engineering of other civilizations. Yet when we listen, we hear nothing but the natural hum of stars and gas. This is the Fermi paradox, the staggering contradiction between the high probability of alien life and the utter lack of any evidence for it. This great silence forces a humbling conclusion. Perhaps the emergence of life itself is an astronomically rare fluke, a series of chemical accidents so improbable that we are truly alone. Or maybe life emerges often, but the leap to complex multicellular organisms is the true bottleneck, a biological hurdle that most worlds never cross. The most unsettling possibility is that of a great filter. This is a barrier, a developmental or existential challenge that arises at some point between non-life and a spacefaring civilization. A challenge so severe that nearly every species that encounters it is wiped out. Is the filter in our past something we have already and miraculously survived? This would mean the evolution of intelligent, self-aware life is the cosmic anomaly, and we are the lucky, lonely winners. Or, more ominously, is the filter still ahead of us? This would suggest that every civilization that reaches our level of technological advancement inevitably discovers something, perhaps in physics or biology, that leads to its own destruction. The silence, then, is not a sign of our uniqueness, but a graveyard warning. Every star we see could be a tombstone for a civilization that once looked up at their own silent sky and wondered the very same thing. A strange and unsettling alignment haunts our most precise map of the cosmos. Buried within the serene uniformity of the cosmic microwave background, astronomers have detected a pattern so improbable it has earned a dramatic name, the axis of evil. This is not a temperature fluctuation, but a bizarre correlation in the way those fluctuations are oriented across the sky. Certain large-scale features, the biggest hot and cold spots in the infant universe, appear to be mysteriously aligned with the plane of our own solar system. Statistically, this should be impossible. The cosmic microwave background is a snapshot of the universe from a time long before our sun or planets ever existed. It is a relic of the entire cosmos, and its features should be completely random, having no conceivable connection to the trivial orientation of our little planetary neighborhood billions of years later. It is as if you found a fossilized dinosaur skeleton, and the alignment of its bones perfectly matched the floorboards in your living room. The correlation makes no sense within our standard model of cosmology. For this to be a real signal, it would suggest that our local frame of reference is somehow special, a concept that directly contradicts the foundational Copernican principle, the idea that we do not occupy a privileged place in the universe. The implications are so profound that many scientists strongly suspect a more mundane explanation, perhaps a subtle systematic error in how we process the data from our telescopes, or an unknown foreground effect from within our own Milky Way galaxy clouding the pristine signal. Some even point to a psychological bias where our pattern-seeking brains are fooled into seeing significance in random noise. Yet, despite rigorous efforts, the anomaly has not been fully explained away. If it is real, it points toward a physics we have not yet imagined, a pre-inflationary geometry to the cosmos, or a fundamental law that somehow links the vast entirety of creation to our own tiny corner of it. The axis of evil remains a ghost in the machine, a whisper that our most perfect cosmic map might still be reflecting our own shadow. One of the coldest places in the known universe is not a distant void, but a specific, sprawling patch on our most ancient map of the sky. This is the cold spot, a vast and profound anomaly etched into the cosmic microwave background. It is not a mere statistical fluke. but a region of space hundreds of millions of light years across that is significantly colder than the surrounding afterglow. For years, scientists have struggled to explain its existence using our standard cosmic recipe. The subtle tug of a vast, empty supervoid lying between us and the cold spot was one proposed answer, a cosmic emptiness so grand that light would lose energy climbing out of its gravitational well, creating a cold imprint. Yet when astronomers meticulously mapped the galaxies in that direction, they found nothing large enough to account for the profound chill. The void was there, but it was not nearly vast or empty enough to explain the temperature drop we observe. This left a glaring, frigid mystery on our most trusted cosmic snapshot. The failure of conventional explanations has opened the door to a truly spectacular possibility. One exotic theory suggests this cold spot is a cosmic bruise, a remnant of a collision with another universe during the epoch of inflation. In this mind-bending scenario, our entire cosmos is just one expanding bubble in a frothing, eternal multiverse. During its hyper-fast infancy, our bubble universe may have grazed against a neighboring one. That colossal impact would have drained energy from the region of contact, leaving behind a permanent cold scar on the fabric of our reality. It is a cosmic fossil of an event that occurred before our universe, as we know it, even truly began. While this idea remains highly speculative and fiercely debated, its mere consideration forces us to confront the ultimate limits of our knowledge. The cold spot stands as a stubborn, frozen question mark, a clue that our universe might not be alone, and that its deepest scars could be the imprints of its cosmic neighbors. Deep within the heart of a black hole, a fundamental law of reality seems to break. This is the black hole information paradox, a puzzle that pits Einstein's theory of gravity against the quantum rules that govern atoms and light. At its core is a simple, profound principle from quantum mechanics, the law of unitarity. This law states that information is never truly lost. If you were to burn a book, its pages would turn to ash and smoke, a seemingly irreversible loss. But in the quantum world, that information, the specific arrangement of atoms that spelled out every word, is not gone. In principle, with a godlike understanding of physics, you could reverse the process, collect every particle of smoke and heat, and reconstruct the book perfectly. Information, in the quantum sense, is forever. Now enter a black hole and Stephen Hawking's stunning discovery. Hawking realized that black holes are not completely black. Due to quantum effects at their very edge, they slowly leak radiation, a faint glow we now call Hawking radiation. This radiation carries away energy, causing the black hole to gradually shrink and over eons evaporate completely. The paradox emerges from what happens to the information of anything that falls in. Imagine you toss our book into a black hole. According to general relativity, the book is lost forever behind the event horizon, crushed into a singularity. According to Hawking's calculations, the radiation that the black hole emits is completely random, thermal noise. It contains no information about the book's contents, its title, or the ink on its pages. When the black hole finally evaporates, all that remains is this random, featureless heat. The information about the book is gone, erased from the universe. This violates the sacred quantum law that information must be preserved. It suggests that our most fundamental understanding of physics contains a catastrophic contradiction. How can the universe just forget? The resolution to this paradox is one of the greatest challenges in theoretical physics, and it almost certainly requires a theory of quantum gravity, a framework that unites the very large with the very small. One compelling idea is that the information is not lost inside the black hole, but is somehow encoded on its event horizon, the point of no return. The falling book's information could be smeared across this surface like a hologram, and then slowly, intricately scrambled and returned to the outside universe in the Hawking radiation. The radiation would not be random after all, but an incredibly complex, encrypted message detailing everything that ever fell in. another radical suggestion is that there is no such thing as a true singularity or an event horizon in the way we classically imagine. The center of a black hole might be a dense, chaotic knot of spacetime, a firewall that instantly destroys anything entering, but in a way that still preserves the information. Solving this puzzle is not just an academic exercise. It forces us to ask what spacetime truly is at its most fundamental level. The violent conditions of the very early universe, moments after the Big Bang, were likely governed by these same quantum gravitational laws. Understanding how information behaves in the most extreme gravitational environment we know brings us closer to understanding the first instance of creation itself, revealing a reality where nothing is ever truly forgotten. The information paradox forces us to confront an even more radical truth about reality's fabric. The solution might be that our experience of a three-dimensional cosmos is a magnificent illusion, a hologram projected from a distant two-dimensional surface. This is the holographic principle, a concept that emerges directly from the strange physics of black holes. When physicists struggled to understand how a black hole could preserve information, they made a stunning calculation. They found that all the information about everything that falls into a black hole is not stored in its mysterious interior, but is perfectly encoded on its event horizon, the boundary that shrouds it from view. The entire three-dimensional volume of the black hole is described by quantum bits of information painted onto its two-dimensional surface. This is like taking a complex three-dimensional object and compressing all its data onto a flat two-dimensional film. When you play that film with the right projector, the full object reappears in all its depth. The holographic principle boldly suggests that our entire universe operates on the same cosmic rule. The space around you, with its height, width, and depth, might be a vast dynamic projection. The information that creates every galaxy, every planet, and every one of your thoughts could be stored on a remote two-dimensional boundary that encloses our cosmic horizon. Think of the world you see on a high-definition television screen. The image has depth and movement, but every detail originates from a flat two-dimensional array of pixels. Our universe could be a similar cosmic display, with the Planck scale, the smallest possible size, acting as the fundamental pixel of reality. If this is true, then the Big Bang was not an explosion in a pre-existing space, but the moment this cosmic projector flickered on, translating a perfect two-dimensional code into the three-dimensional world we inhabit. This principle provides a powerful new language for describing the quantum structure of spacetime itself, suggesting that gravity emerges from this intricate, information-based geometry. We are, in a very literal sense, living inside the most complex hologram imaginable, a ghostly image of a deeper, simpler reality written on the edge of the visible world. Perhaps the most disorienting clue is that time itself may be an illusion. Our lives are defined by its relentless flow, from the beating of our hearts to the aging of stars. Yet when we push our fundamental theories to their limits, this river of time seems to vanish into a static landscape. The equations of general relativity, which describe the cosmos, and those of quantum gravity, which attempt to describe its birth, often work perfectly without time as a fundamental ingredient. In these rarefied descriptions, the universe is not a movie playing out frame by frame, but a single, frozen snapshot containing all moments at once, past, present, and future. This is the problem of time, a profound disconnect between our lived reality and the bedrock laws of physics. How does the vivid, flowing now we all experience emerge from a timeless foundation? One compelling idea is that time is not a primary feature of the cosmos, but a secondary, collective phenomenon. Think of the temperature of a gas. A single atom does not have a temperature, it just has speed and direction. Temperature only emerges when you have a vast collection of atoms jostling together, a property of the crowd, not the individual. In the same way, our experience of time's flow might emerge from the complex interactions of countless quantum particles. It is a story the universe tells itself through change and relationship. The ticking of a clock, the burning of a star, even the process of thought are all about comparing one state to another. Without change, there is no time. This suggests that the Big Bang was not an event in time, but the moment time itself, as we understand it, began to unfold from a timeless origin. Your deepest feeling of a present moment of things happening now could be the universe's most beautiful and persistent magic trick, a necessary story woven from a deeper, silent reality. This single, perfect balance of our universe might not be a miracle, but a simple matter of statistics. If the force of inflation is truly eternal, then the moment of hyper-fast stretching that birthed our cosmos never truly stopped everywhere. It is a fire that cannot be extinguished, a process that continues eternally in a sea of primordial energy, spawning new universes like bubbles in a vast, boiling cauldron. Each of these bubble universes inflates and pinches off from the background, becoming its own separate, self-contained reality. The critical detail is that in each of these cosmic bubbles, the random quantum processes that settle the fundamental laws could play out differently. The strength of gravity, the mass of an electron, the number of spatial dimensions, all of these fundamental constants could be randomly locked into a unique configuration within each new bubble. In this infinite multiverse, every possible set of physical laws would be realized somewhere in some universe. Most of these universes would be stillborn, chaotic voids where atoms never form or where matter instantly collapses back into energy. They would be cosmic dead ends, dark and lifeless. Our universe, with its precise balance that allows for galaxies, stars, planets, and life, would not be special or designed. It would simply be one of the rare habitable bubbles in an infinite froth of uninhabitable ones. We won the cosmic lottery, not because the odds were in our favor, but because in an infinite multiverse, every possible outcome, no matter how improbable, must happen an infinite number of times. This idea pushes the Copernican principle to its absolute limit, suggesting that not only is our planet not the center of the universe, but our entire universe is just one unremarkable specimen in an unimaginably vast collection. While we have no direct evidence for other bubbles, the multiverse emerges as a natural, if speculative, consequence of our leading theory of the beginning. It transforms the question of why our universe is so finely tuned for life from a profound mystery into a simple observation. Of course, we find ourselves in a universe that can support us. We could not exist anywhere else. The great silence of the cosmos, the eerie fine-tuning, and even the bizarre initial conditions we have explored could all be echoes of our cosmic address within an infinite, bubbling meta-reality. The newest and most startling clues are arriving right now from our most powerful window into the past. The James Webb Space Telescope is peering back to the cosmic dawn, to an era just a few 100 million years after the Big Bang, and it is seeing the impossible. These infant galaxies, which should be small, fragile, and only just beginning to form, appear instead as cosmic giants. They are massive, mature, and brimming with stars, looking as if they have been evolving for billions of years, not a scant few 100 million. It is like finding a fully grown adult in a nursery of newborns. According to our most trusted models of galaxy formation, there simply has not been enough time for gravity to pull together such immense structures so quickly. The dark matter scaffolding needed to build them should still be coming together, not already hosting glittering cities of stars. This is not a single anomaly, but a growing pattern in the data, a chorus of ancient galaxies all telling the same strange story. Their very existence suggests that something is missing from our timeline. Perhaps the first stars ignited far earlier than we ever thought, in a darkness more profound and productive than we imagined. Maybe dark matter behaves in a way that accelerates the growth of these cosmic structures, clumping together with unexpected speed. Or perhaps our entire understanding of the universe's first chapters needs a fundamental rewrite. Every new image from Webb is a live transmission from the edge of our knowledge, a direct challenge to our cosmic story. This is not a settled fossil, but a clue still warm from the forge of creation, one that may ultimately force us to redraw the very first pages of our universe's history. From the faint hiss of the cosmic microwave background to the impossibly mature galaxies seen by the James Webb Space Telescope, each clue is a testament to our relentless curiosity. We have traveled from the first fleeting moments of nucleosynthesis to the silent grip of dark matter, from the violent stretch of inflation to the ghostly whispers of gravitational waves we have yet to catch. These are not just isolated facts, but pieces of a grand, interconnected puzzle. Some pieces fit together with breathtaking elegance, confirming our deepest theories. Others, like the stubborn lithium problem or the unnerving Hubble tension, stand as stark reminders that our map is still incomplete. This is the true nature of cosmic discovery, a journey where every mystery solved reveals two new questions waiting in the darkness. The story of our universe is still being written, and each new observation, whether from a telescope on a remote mountaintop or a satellite orbiting in the void, adds another line to the epic. We have learned enough to be humbled by the vastness of our ignorance and to be inspired by the infinite possibilities that remain. The greatest clue of all is that the cosmos is still speaking if we only continue to listen.